smaller by the day. That's okay, as long as they're watching the YouTube videos. All right, well, good morning, everybody, and welcome back to Math 115. So, let's see, before we get started, how's everybody doing? Are we thriving? Not thriving. How come? Morgan's making it. Same. I hope you mean same as in making it. Okay, good. Yeah, I don't know. I feel like I'm in kind of the same boat. My grad classes are all like sort of intense, and I have no clue what's going on in most of them. So it's like pushing your car after it's run out of gas. Yeah, that's a good analogy. Okay, well, hopefully we can find something relatively ready for summer already. It's February. Okay, all right. Yeah, summer's nice. No classes. Maybe get an internship or something. Just chillax. Yeah, not having spring break is hard. I have to say. They put the wellness days throughout the semester or whatever, but I feel like it still just doesn't really make up for it, to be honest. Yeah, and no cold, yeah, in the summer, that's true. Yeah, I'm from Indiana, so I'm used to very, very cold. A lot of teachers will still assign work just to a day later than the wellness day. Ah, so you wound up having to spend the wellness day working on homework? That sucks. I'm trying to think. Maybe I should move my homework due date. Do people want me to move the homework due date for this week so that it's not on Friday, the day after the wellness day? It's kind of a big window, though. I feel like. I mean, okay. Maybe I'll think about it. Okay, I'll think about it. All right. Well, let's get started on some math stuff then. And I guess let's start by reviewing the announcements and what we did last time, okay? So just a reminder, homework 4 and 5, okay, because of the glitch on my math lab, which caused people to not be able to work on the homework on Friday night, I extended the deadline to Tuesday, February 23rd. That's today. So you have until midnight tonight to keep working on that. So if you forgot to do the homework assignment last week, you're in luck because it got extended. And otherwise, disregard that announcement. No class this Thursday on the wellness day. Again, I'll think about what to do with the homework assignment. Maybe I'll extend it. We'll see. And then I'll have regular office hours this week. So I had my office hours yesterday. Nobody came. Nobody ever comes. And I'm really lonely during office hours. I wish somebody would come and at least keep me company. No, I'm just kidding. I don't care if you keep me company. But I really want to highlight the fact that I have these office hours and I'm available and I can help you before you get behind, okay? Or as you are starting to get behind. So I just want to mention, and this is not me being like a hard ass or anything, it's just that the material that was on the first exam was primarily sort of review material, okay? And since that time, we've done a lot of kind of new things that you may not have ever seen before in your other math classes. And exam 2 and 3 and the final exam typically in a class like this, we see really high scores on the first exam, and then the second exam and third exam, not so much. So I just want everybody to be aware that I'm here and ready to help you. And the best time to get help is before you realize, oh crap, I needed help. So please come to my office hours on Wednesday if you feel like you might be getting a little bit behind. Okay. And exam 2 is on March 8th again. Okay, so that's all I have to say about announcements and administrative stuff. So what did we talk about last time? We talked about logs, okay? And I tried to take everybody through this kind of logic at the start, which I'm not sure this totally landed as well as I wanted it to land. But basically what we did was we looked at the graph of an exponential function, and we noticed that because it passed the horizontal line test, that the graph was 1-to-1. Okay, and back when we learned about one-to-oneness, okay, we learned that if a function's graph, or if a function in general is 1-to-1, then we can find the inverse function. That was the consequence of a function being 1-to-1, is that there is an inverse. Okay, it's not always true that there's an inverse. Okay, take for example, y equals x squared, has no inverse. You can take the square root function, but that only gives you one of the values which the inverse would produce. Okay, so one-to-oneness tells us that we have an inverse. Okay. And so then the rest of the lecture was on, okay, what is the inverse of an exponential function? And the inverse of an exponential function is what we call a logarithmic function. Okay, so a logarithmic function takes the output of an exponential function, okay, and it maps it to the input that you would be able to plug into that exponential function and get that output. Okay, that's what's going on with a log function here. Okay, so this log a here is taking this x, which was the output of our exponential function when we plugged in y. And the output of the logarithmic function is this y here, which is what our original input was in our exponential function. Okay, so it's sort of doing the reverse thing of what an exponential function does. Okay, and we have a whole family of functions like this. For every number a here, which is larger than 0 and a not equal to 1. Okay, so we can do like log 2 of x, we can do log 5 of x, we can do log e of x, we could do log 1/2 of x, and so on and so forth. Okay, so this is what a logarithmic function with base a is doing. Okay, so then we had some practice converting between these two forms. Okay, and we basically just switch. Okay, when we have like 4 cubed equals 64, we rewrite it. The base, okay, goes where the base is. The exponent goes on the opposite side, and then the argument goes inside our parentheses. Okay, so before we were plugging in the number 3 into the equation 4 to the x, and we got 64. Now we plug in the number 64 into the function log 4, and we get 3. Okay, so it's kind of reversing. So first we went from 3 to 4, or 3 to 64 by means of the function 4 to the x. And meanwhile, log 4 took 64 to 3. Okay, so these are doing the opposite thing, okay? going on with logs? All right. So then we did some more examples of switching back and forth. And I just want to highlight this last example here because a lot of the times we wind up with a problem like this where we actually can use our switching between the exponential form and the logarithmic form to find out what an unknown variable is. Okay? So in this particular case, if we want to know what log 2 of 8 is, I mean, we could use a calculator and figure out what the left-hand side is. But if we don't want to do that, we can rearrange it and write it as the exponential equation. We know if we plug 8 into log 2, we get x. That means if we plug x into 2 to the x, we get 8. So we switch the form, and we recognize that there's only really one number. There's one familiar number, which we could plug in for x here, which would get us 8. Okay, and that's x equals 3. Didn't I write that down? I guess I didn't write that down. Okay, so there's one number which we could plug into here to get 8, and it's 3. Okay, so we can use this kind of switching back and forth to solve for variables which are in our equation. All right, so how do we evaluate logs? Well, basically, all we do is we can either rearrange into the exponential form and then kind of figure out what x is going to be because of that. Okay, which is what we did here pretty much every time. Or we can use a calculator, okay? Or if you want, you could use a log table, but people don't really do that anymore. Okay, and the special property between f of x equals a to the x and f inverse of x, which is log a of x, is, well, if we have inverse functions and we plug one into the other, then we get the same thing which we originally started with. Okay, so we start with x, we plug it into a to the x, and then we plug that whole thing into log a of that thing, and we get back our original input. Okay, so the original input is x. We plug it into log a of x, and we plug that into a to the power of something, and we get back our original input. Okay, that's what it means for these functions to be inverses. All right, and then we had 4 basic properties. We're nearly caught up. The properties that we had were that, well, if we do the log a of a, so if the base and the argument are the same, we just get 1. Okay, that's because the exponential equation would be just a to the 1 equals a, which is true. Okay. Log a of 1, okay, the corresponding equation would be a to the 0 equals 1, so 0 should go on the right-hand side of this equation. And then we already sort of saw this, but since log a of x and a to the x are inverses, if we do log a of a to the x, we get x. And if we do a to the log a of x, we get x. Okay, that's what it means for these functions to be inverses. Okay, so let me quiz you guys. Well, not a quiz for real, but let me just perform some kind of like informal check here to see how we're doing with this stuff. Let me ask everybody, how would we solve, or how might we solve I don't know, how about 9 equals log 3 of x? No, let's do, this would be 2, let's do 2. 2 equals log 3 of x. So our goal is to find x. So what should we do here? If we want to use some of what we've learned so far to solve this equation 2 equals log 3 of x. We want to find out what x is. How can we solve this? Yep, that's definitely one thing we can do. Yeah, so there's two things we can do. We can, I like that that Savannah and Morgan both put these two answers in here because they highlight kind of two different perspectives we can take. Okay? Perspective one is as follows. And I think that this is what Savannah is alluding to, but it's kind of hard to tell just from looking at the chat. But perspective one is to just use the definition. The definition of when we define what it means for a log, what a log function actually means is we would say that 2 equals log 3 of x if and only if 3 squared equals x, and therefore 9 equals x. Okay? So that's perspective one. We can just use the definition to rewrite this in exponential form. Okay? Perspective two is sort of the same thing, but it might be a little bit more familiar to some students. Perspective two is to simply manipulate each side and use our rules. So how would I do that? What I could do is I could just say, okay, I have 2 equals log 3 of x. And as long as I do the same thing to both sides, this equality is going to stay true, right? Like, for example, I could multiply both sides by 6, and the equality would stay true. Okay? So I'm going to use this kind of process to figure out how I can solve this. So the process that I'm going to do is I'm going to basically take both sides and use them as the exponent in 3. Okay? All I've done here is I said, okay, a is equal to b, therefore 3 to the a is equal to 3 to the b. All right, this is good logic here. We can say that. If we have the same, if we have two numbers which are equal and we take the same number to those two powers, we're going to get the same thing. Okay, so this follows logically. All we've done is taken both sides and put them in the exponent on 3. Since these two things were equal to begin with, when we take 3 to the same power, we get the same thing, and this is still an equality here. Okay, and now what do we recognize? The left-hand side is just 9, and the right-hand side looks like 3 to the log 3 of x, right? And that was one of our rules. I think, in fact, that was rule number 4. We said a to the log a of x is equal to just x. So we have something which looks just like that. We've got 3 to the log 3 of x. So all I've got here is x. Okay, so those are sort of two perspectives which you can take. I mean, they're really sort of doing the same thing, ultimately. But some people really like using perspective 2 because perspective 2 may be more familiar in terms of manipulating equations. Okay, for Algebra 1, Algebra 2, all of the stuff that you learned before you came to this class, you do a lot of this business of, okay, just do the same thing to both sides and then move things around and make sure that you're just keeping the equality true. So if you want to use that method, that's a good one too. Okay, so that's two different perspectives on how we might solve this log problem. Any questions on this problem here? By the way, I was thrilled to find out yesterday that there's actually a second page of colors on Notability. So, I don't know. I'm not sure I like this red because it's not super visible. At least when I look at the teams, it looks worse than it looks on my iPad. So if there's ever anything that you can't really see because of the color, please let me know. I like this cyan color though. All right, so we'll have some more examples here. So how can we compute log 3 of 3? What should we get when we do this one? We can just use one of our rules here. We don't need to go to the trouble of rewriting this in an exponential form. What should we get when we do log 3 of 3? I mean, yeah, it's going to be 1. I can rewrite this as log 3 of 3 to the first power, right? Remember when we do log a of a to some power, we just get the power. So it's just going to be 1 here. Seems like once Abdul Rahman put in his answer, everybody felt a little more confident in their own. That's good. That's okay. I do that too in my classes where I'm like, I type something out sometimes when my professors will ask a question and I'm like, I'm just waiting to hit send until I hear somebody say something like along the same lines and I'm like, oh yeah, I thought that too. All right, how about log 7 to the log 7 of 5? What are we going to get for this one? Can we use another one of our rules here? Yeah, we can just type out, we can just do 5, right? We see we've got log 7 in the power of 7 to the log 7 of something. We're just going to get that number here, right? This is the inverse property. Okay, so that's a couple examples there. So now let's talk about the domain and range of the function f of x equals log a of x. Okay, and I'm going to talk about the domain and range by talking about the graph. So here's a to the x. What does it look like? It goes through 1 comma a, and it goes through 0 comma 1. And it looks something like this. There's a to the x. And here is a line. Oh, why don't I use green? I don't know. This is the line y equals x. Okay. And I should switch colors again. Maybe pink. The graph of log a of x, what is it going to look like? Well, it's going to be symmetric across this thing. Okay, symmetric across y equals x. So in particular, for every point a, why don't we call it h comma k? On our graph of log a of x, we are going to have the point k comma h. Okay, that's the property of an inverse function. And it looks something like this. Okay, it looks like this. So if we want to talk about the domain and range of log a of x, we can be a little bit clever, okay, and just remember about what the domain and range of a to the x are. So if I know the domain and range of a to the x, then based on this property of the way that I get the graph of log a of x from a to the x, I can find out what is the domain and range of log a of x. So this is my clever trick. I say that a to the x has x values, that is the domain, which are any real number. Now, what does this tell us about, what can we now conclude about log a of x? So my question for you all is, what can I put in here in this green box here? We know that a to the x has x values, which are just anywhere along the x-axis. Whoops, wrong button. So what is that going to tell us about log a of x? Okay, you're right, Abdurrahman, but that's getting a little bit ahead of ourselves. I just want to say, for a to the x, we know something about its x values. And we know that an inverse function, the x values from our original function become the y values. So if we know where the x values of our original function lie, what's that going to tell us about our new function log a of x, which is an inverse of that function? I get the sense that maybe some people have an idea, but they're not quite confident enough to put it out there in the chat. And I guess what I would say to you is, this is a safe space, okay? If you're going to be wrong in the chat, nobody is going to judge you, okay? It's totally fine. In fact, making mistakes in math is one of the best ways that you can possibly learn. If you can have the courage to make mistakes in lecture, even more so. Yeah. Yeah, so we get all real numbers here for the range of log a of x. So let me describe why. We can see here that, and my graph is getting a little bit crowded. Maybe let me switch to highlighting in yellow. Okay, we can see by looking at the graph of a to the x, okay, looking at this graph here, we just look and see, where do all of the x values lie? The x values of our graph are just everywhere along the x-axis, okay? Now, if I were to take this x-axis and reflect it about this, this line y equals x, okay, well, the reflection of this orange piece here would come right here. And the reflection of this blue piece here would come right here. So what this is saying really is that since all of the y values of log a of x are just the x values of a to the x, and we know that all of the x values of a to the x are just all real numbers, then we know that the y values of log a of x is also all real numbers. Which is to say that if we know something about the domain of a function, then that is going to tell us about the range of the inverse. Okay? So here we're going to see that the y values, in other words, the range, are going to be all real numbers here. Okay? And that makes sense. Just look at the log graph. It's going up, 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 and down, 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 down to the left, right? If we were to consider the range, that's the set of values on the y-axis, such that if we drew a horizontal line, it would intersect our graph. Well, it's going to be every single horizontal line that we could possibly draw, right? Because it goes, this log function just goes up, up forever, and also down, down forever in the other direction. Okay. For the same reason that a to the x goes left forever on the left-hand side and right forever on the right-hand side. So that's how these things correspond to one another. And likewise, and I think this is what Abdurrahman was kind of hinting at earlier, likewise, what are we going to have? We also have a to the x has y values in 0, infinity. And that's telling us that log a of x has x values. In other words, its domain in the same space, 0, infinity. Okay, and we can see that's true because where do we see our log function sort of existing here? Only to the right of the y-axis. Okay, and as we go down, 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 we get really close to the y-axis, but we never touch it. Okay, that's because on a to the x, we get really, really close to the x-axis and never touch it. Okay, so this is how we can find the domain and range of log a of x. So the domain is just going to be 0, infinity. And the range is going to be all real numbers. So let me pause and ask, is this sort of clear, or is this really a little bit hand wavy and confusing? Or somewhere in the middle? I'm just looking for a little bit of feedback so that I know whether I should keep talking about this some more or move on. I think it makes sense. Okay. You can always refer to this picture here if you get confused. As long as you know what the graph of a to the x is, and you know the fact that an inverse function just gets reflected across this line y equals x, then you'll be able to find a pretty good picture of what the function, the log function, should actually look like, and then from there kind of see if you can suss out what the domain and range are. You can also just memorize the fact that the domain and range of log a of x are going to be these two things, and that's also fine. But I like to try to give some kind of intuitive like reasoning for why the things that I say are true are true. I don't want you to just believe me. I want you to kind of believe it for your own reasons. All right, so one thing that I put in red here, and this is just something that I want to remind you guys of. Okay, when we write log a of x, this log a thing here, okay, this is a function. Okay, this is like f of x. Okay, or g of x. Okay, where you can think of us replacing f or replacing g with log a. Okay, so a common mistake that I want you guys to avoid is something like the following. A student might see the equation 3 equals log 4 of x, and they might say, okay, therefore we just divide both sides by log 4, and we get 3 over log 4 equals x. Done. Okay. This is not, let's just say, if I see this while grading, this does not spark joy. This sparks the opposite of joy. Okay, so when we have log 4 of x, we need to remember this is a function. Okay, so we don't undo functions by dividing. Okay, i.e., if we have y equals f of x, this does not imply that y divided by f equals x. That's not how this works. Instead, what we need to do is y no, not y, sorry. Instead, what we need to do is the following. We would do y equals f of x, and the way we undo this function is with its inverse. Undo a function with its inverse. So we would apply the inverse function to both sides. And we would recognize that if we plug something into a function and then we plug that number into the inverse of that function, then we get just x on this side. Okay? This is how we undo functions. So please don't divide by log 4. This is sort of nonsensical. If you put log 4 here in the denominator, it just makes no sense at all. This makes no sense. Because log 4 is a function, and we don't know how to divide a number by a function. They're not compatible in that way. So rather, what we should do, the right way, would be to do something like this. If we had, what was the equation? 3 equals log 4 of x. What we should do is use the inverse function on both sides. We would get 4 cubed equals 4 to the log 4 of x. And then we would get 64 on this side. And on this side, we would just get x. This one sparks joy. All right, so that's just a word of warning. which is just like a really common mistake that I see when I teach classes like this. And even when I teach calculus, sometimes I still see students doing this. So it's just a really common, easy trap to fall into that I want you guys to be aware of, so that you guys don't need to fall into that trap. Okay. So let's talk about graphs of log functions. Okay, and graphs of log functions we can do in one of two ways. We can just take the graph of its inverse, g of x equals 2 to the x, and flip it. Okay, so we could just take 2 to the x here. Whoops. And we can take every point which is on 2 to the x, and we can take h comma k, and we can then just flip it across this y equals x, and we'll get the points like k comma h. Okay, you can do that. Or we can just try getting various values of log 2 of x. So let's try plugging in with this table. So first we could get log 2 of 1. Okay, so log 2 of 1, this is going to be the number y such that 2 to the y is equal to 1. In other words, log 2 of 1 should be equal to 0. Okay, here we would have log 2 of 2. In other words, we're talking about the number y such that 2 to the y equals 2. And that means that this is going to be equal to 1. And so on and so forth. We'd get log 2 of 4. That's the number y such that 2 to the y equals 4. Well, that should be equal to 2. And then we should get log 2 of 8. Well, that's going to be equal to 3. And then these ones, log 2 of 1/2, we have to be a little bit careful. This would be the number y such that 2 to the y equals 1/2. So what should y be? If 2 to the y equals 1/2, what is y? Okay, let's try it. Let's try some of the ones we got in here. I'm seeing some 1/4, some 4, some 1/4. Let's try. If we do 2 to the y equals 1/2. Well, if we plug in 1/4, we would get 2 to the 1/4 equals 1/2. And remember, a 1/4 power is the same as doing a 4th root. So we would get the 4th root of 2 is equal to 1/2. And if we just took both sides to the 4th power, we would get 2 on this side. And then on the right-hand side, we would get 1 over 2 to the 4th, which would lead us to 2 is equal to 1 over 16. Okay, so I don't think that 1/4 is going to work here for the following reason. 1/4 would work if we were doing 2 times y equals 1 to the 1/2. This would be, yes, y equals 1/4. But here we've got y in our exponent, okay, and that's going to cause some trouble. Oops. Okay, so this one didn't work. Now we could try 4, I think was also suggested. But if we have 2 to the y equals 1/2 and we plug in 4, we'd get 2 to the 4 equals 1/2, and that would be 16 is equal to 1/2, which again fails to be true. So what should this y value be here? We want to know what power of 2 could we take and we get 1/2. It's kind of tricky. Yeah, that's the one. We should use -1, right? Remember, 2 to the -1 would be equal to 1 over 2 to the power 1, where the 1 is positive, right? If we have a negative power, what we do is we move that number to the denominator and we make the power positive. And 2 to the 1 is just 2, so this is equal to 1/2. So this is the right way to do this one. Okay? So don't forget about those negative powers. That's how we get fractions when we're using an a value which is larger than 1. If we want to have eventually an output which is less than 1, we should be using a negative power here. Okay, that's how we should do that one. So here we should get -1. And then how about for 1/8? If we want to get 2 to the y equals 1/8, how should we do that one? What should y be here? I think it should be negative again. Yeah, Jake's got it. -3, right? Because then 2 to the -3 would be equal to 1 over 2 to the 3 would be equal to 1 over 8. So that's how these negative powers work, and they give us these numbers which are smaller than 1. So here we would get, for 1/8, we would get the y output would be log 2 of 1/8. And remember, when we write log 2 of 1/8, we're talking about a number, okay? We're talking about a number, and the number we're talking about is the number y that makes the equation 2 to the y equals 1/8 true. And that number is -3. So let's do some graphing. We have a bunch of points now. So our x value, when our x value is 1, our y value is 0. So we should have a point right here at 1, 0. When our x value is 2, our y value is 1. So I guess I should put some, where we go up to 3. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so when our y value is, or when our x value is 2, our y value is going to be 1. So we just put a point at 2, 1. I hate it when that happens. 2, 1. And then when our x value is 4, our y value is 2. Here we are up at 4, 2. And then 8's not on our coordinate axis, so I guess we will get rid of that one. But then we've got 1/2 and 1/8. Okay, so when our x value is 1/2, our y value should be -1. So at 1/2, our y value is -1. So I'll just put a point right there. And when our y value is 1/8, our x value is 1/8, then our y value should be -3. So when we're at 1/8 there, we're all the way down here at right there. Okay, and we just draw a smooth curve connecting all these points. It should look like the log curves that we've been drawing so far. And in this case, it looks something like this. So there's the graph of f of x equals log 2 of x. We can plug these numbers in, right? And you can also just recognize that this table here is the reverse of the table, which looks like x and 2 to the x. okay? So here we would get like, I don't know, 1, 2, 3, 2 to the x would be like 2, 4, 8. Okay? We can just take these things on top and say, okay, instead of thinking this, I'm going to take that to be x, and I'm going to take this to be log 2 of x. Bam, done. Okay? So log 2 of 2 is 1, log 2 of 4 is 2, log 2 of 8 is 3, right? That's what this function does. It's the inverse of 2 to the x. Okay, so that's two ways you can do it. You can evaluate the logs, or you can just find the table for 2 to the x and flip everything over. Any questions about graphing log functions? By the way, I just realized I went back to using this blue, and I don't think the blue is very visible. Sorry, I meant to be using the cyan. All right, if no questions, we're gonna keep trucking. Let me see where we're at. Okay, we got a little bit more to go through today. Oh yeah, two facts. So this is analogous to the facts that we had last time. In fact, I even wrote them down. Okay, so the facts we had for exponential equations were that if we have y equals a to the x, then 0, 1 is going to be on the graph, because if we plug in 0 for x, we would just get a to the 0, and that's 1. Okay, so what does that tell us about the log function? Well, the log function is going to have the reverse of this point on the graph, right? If this is our h comma k, then we should have k comma h on the graph of log a of x. Okay, so every log function, which is untransformed, will pass through the point 1 comma 0. And we saw that was true with our graph up here, right? We have this point here, 1 comma 0. So this is kind of like a way you can pin down one point. All right, and the other point we get is again from the same equation, right? Before we had y equals a to the x. Then we said, okay, well, if we just plug in 1 for x, then we would just get a to the power 1, and we just get a. So we know that 1 comma a is on the graph of a to the x, and therefore we know that a comma 1 is on the graph of log a of x. Okay, so in our case, we had 2 comma 1 here. Okay, so this was 2 comma 1, and this was 1 comma 0, right? And those were the reverse of those 2 points, which we would have had on 2 to the x. We would have had 0 comma 1, and we would have had 1 comma 2. So this would have been the graph of like 2 to the x, okay? This would have been 1 comma 2. This would have been 0 comma 1. So those were the 2 points which we sort of nailed down, and we said, okay, we know for sure these 2 points are going to be on our exponential function, and that's kind of one way in which we can like sort of draw a reasonable looking graph just by plotting those 2 points and, okay, draw an exponential function which goes through them. And basically, these are going to correspond to 2 points on the graph of the log function, because after all, the log function is just the inverse of this exponential function. So that's these two facts. It's just about how we can guarantee 2 points which are going to be on the graph of log a of x. Okay. So next up, copied in this table again, just because, believe me, I cannot write out this table in a way that looks this good. So let's just go through what it's saying. All it's saying is the usual business about transformations, okay? If we add something out back, what does that do? Shifts us up C units. If we subtract something out back, what does that do? Shifts us down C units. If we subtract something inside, it's going to move us to the right C units. If we add something inside, it's going to move us to the left C units. And this is all really just the same as all the transformations which we've ever done. Okay, if we multiply by a number out front, depending on whether C is larger than 1 or less than 1, we're either going to have a vertical stretch or a vertical compression. If we multiply by C on the inside, depending on whether C is larger than 1 or less than 1, we are going to have either a horizontal compression or this should say horizontal stretch. No. This should say, it should be compress and then stretch. Yeah, this should say stretch here. So, okay, the book has an error. Stretch. Now it's making me paranoid. I better check the rest of these things. Vertically stretch of C larger than 1, yes, okay. Negative log A of x should reflect across the x-axis. Okay, yeah, so if we have negative log A of x, what does that do? We just reflect across the x-axis. And if we have what is with this? This table has errors in it. Okay, so negative log A of x should indeed reflect about the x-axis. And this one over here, I don't know what this negative sign is doing. Just ignore that. It should just say log A. Wait, hang on. Does that even make sense? If we did that, we would have 2 to the, wait, log 2 of negative x does not even make, oh, it does make sense. Yeah. Okay. Man, I can't believe the book has so many errors in it. Okay, so this minus sign shouldn't be here. That's the long short of it. Get rid of that thing. We should just have that log A of negative x, okay, is going to reflect the graph of y equals log A of x about the y-axis, okay? So in that case, we would have log A of negative x would look something like this. Yeah, like that. Whereas negative log A of x would look something like this. Okay, we reflect about the x-axis. Okay, well, bad book, sorry. So those are the usual transformations, okay? So, why don't we just open up Desmos and we'll see how does this transformation look when we transform the function log 3 of x. So let's get Desmos open. Okay, so here I've drawn the graph of log 3 of x. What does it look like? Well, it just looks like this. Basically, it goes through this point here, 1, 0. It also goes through the point 3, 1, as you can see. So if we drew another graph in green and we made that graph like the transformed version, we're going to make it 10 times log 3 of x, and then I think it was plus 2 on the inside. So what is the effect? Well, we shift the whole thing to the left 2 units because we added on the inside of those parentheses. So we move everything to the left 2 units, and you can see for that reason we pass through not the point 1, 0, but the point negative 1, 0. And then what do? We just vertically stretch by a factor of 10, okay? We just vertically stretch this thing by a factor of 10. So every point on the graph of 10 log 3 of x plus 2 should be 10 times as high or 10 times as low as the other ones. Okay, so this is how we kind of transform these functions. Same as the usual business. Okay, so there's two important logs which we should talk about, which are as follows. If we see something which just looks like this, we just see log of x, and you're confused because what the heck, there's no number in this red circle here. We should have a number there, right? But we don't have a number. Okay, this is just a convention that mathematicians use. Okay, if we write log of x, we kind of mean log 10 of x. Okay, so if we don't specify a number, the number is 10. Okay, and we call this log the common log. Okay, it's used all the time in statistics when people make graphs on a log scale. Okay, they use log 10 or the common log. Okay, so common just means 10. Now, on the other hand, what does natural log mean? Well, the natural log, we write ln of x, and that is defined to be log base e of x. Okay, and the special thing about the natural log is it's the log function which is associated with this special number e. And the special number e is associated with the special function e to the x. And I've been sort of purposefully vague about why it's so special. And that's just because it's sort of outside of the purview of this class about why it's special, but it is special, and you should be aware of its existence. And you'll notice that you probably have a button on your calculator which has ln of x. Okay, so your calculator might not have a button for doing like log 2 of x or log 7 of x or log whatever of x, but it will almost definitely have a ln button. Okay, and so this is why you need to be aware of it in conjunction with one more fact which we're about to learn. No, we're not. Actually, we're going to learn it next time. I'll come back and talk more about the natural log later. But for now, just be aware that when we write ln of x, what we mean is log base e of x. Okay? All right. So here we have a couple example problems, some random stuff. And we're just going to go through these problems, basically. That's what we're going to do. So we're just going to try to apply some of the knowledge that we've accumulated so far about logs. Okay. And we're going to try to derive a lower and upper bound for ln of 3 is equal to x. Okay. So what I mean when I say derive a lower and upper bound for this, okay, what I mean is I should eventually, after some work, be able to write something of the form x is less than blank and larger than blank. Okay, so how could we try to take a crack at this problem? We want to derive a lower and upper bound for ln of 3 is equal to x. Well, I know that ln of 3 is really just the same thing as log e of 3, right, is equal to x. Let me switch my color back to something more visible. Okay, so I have log e of 3 is equal to x. And what I might try to do is take both sides to the power e, or rather make them both the power of e. So I will rewrite this as e to the log e of 3 is equal to e to the x. And now I know that e to the x and log e of x are inverses. So I know that this business here is going to cancel, right? And I'll be left with 3 is equal to e to the x. And so let me ask you guys, what do we think are some numbers which we could put in here and here? Based on this equation here, we have 3 is equal to e to the x. It's going to be hard for us to figure out what exactly x is because remember, e is some number like 2.718 dot dot dot, right? In fact, we could even write that. Right, 3 is equal to some number like 2.718 dot 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 to the power x. Okay, so it's sort of hopeless right now for us to figure out what x should be just from looking at this, but we can figure out some kind of upper and lower bound for where we think x should lie in some range between two numbers. Anybody have some ideas for what we could plug in for an upper bound? A number that x should be less than in order for this equation to be true. Yeah, I think 2 would be a good upper bound, right? Let's see why. If x is larger than 2, move this over a little bit. If x is larger than or equal to 2, then 2.718 dot 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 to the x is going to be larger than or equal to 2.718 dot 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 squared, right? If we take a larger power, we get a larger number. And 2.718 squared, well, that's going to be something larger than or equal to 4, right? Okay. So if x is larger than 2, then this number, 2.718 to the power x, is going to be larger than or equal to 4. So if x is larger than or equal to 2, we know this equation can't possibly be true because the right-hand side is larger than 4, and the left-hand side is equal to 3, and we have an equal sign. Okay, so we should definitely say that x should be less than 2. Okay, that's an upper bound for the x value. Okay. Now, what kind of lower bound could we have? Using similar logic, what kind of lower bound could we arrive at? Again, the statement I'm trying to make here is that x should be larger than this number in order for this equation to have a chance of being true. Okay, if we put 3 here, we might be in a little bit of trouble. Okay, because if x is larger than 3 but less than 2, then there's no numbers of x in that interval. Okay, so this should probably be a number which is less than 2. This number should be less than 2. Okay, and I think Aeon's got it again. It should be 1 in here. Okay. Here's the reason. If x is less than 1, then 2.718 to the power x is going to be less than or equal to 2.718 to the power 1, which is equal to 2.718. So if x is less than 1, then the right-hand side of our equation is going to be less than 2.718. And if this number on the right-hand side is smaller than 2.718, it can't possibly be equal to 3. So that's the game we're kind of playing here, all right? It's just about determining a number for which we know x should be larger than that number, and determining a number for which we know x should be less than that number, okay? And that just comes from plugging into this equation, okay? If we make x very large, 2 to the 2 point something something to the x is going to become way bigger than 3, okay? Of course, the directions for this problem were somewhat unspecific. So we could have also just said x should be less than infinity and x should be larger than negative infinity if we were being really cheeky. All right. Sometimes I catch myself on exams giving questions like that, and a student will come up with something really clever, and I have to give them all the points because I didn't cover my butt properly. Okay, so this is just one application of how we can sort of handle deriving a lower and upper bound for this function, or for this equation. We want to derive a lower and upper bound for the value of x based on our understanding of the fact that 2.718 is somewhere between 2 and 3. We just say, okay, well, the number x should be somewhat larger than 1, so that 2.718 should be larger than 2, or 2 to the x should be larger than its original value, but not so large as to make this thing balloon out of control. Okay? So the actual true value of x, which makes this equation 3 equals 2.718 to the power x true, is a value x, which is somewhere between 1 and 2. Okay? It'll be some decimal between those two numbers. Okay, so that's a way we can do this without even using our calculator. We can just figure out kind of where, in general, this is going to lie. All right. So I'll do one more example, and then we'll call it for the day. The example is the following. How long will it take to double your money if an investment earns a nominal rate of 6.5% interest compounded continuously? Okay, so we want to know how long it's going to take us to double our money. So this is going to call back our equation from the other day. Remember, if we compound interest continuously, then the equation for the amount of money in our account is going to be equal to the following. We'll have A of t is going to be equal to our original amount of money, A of 0, times e to the RT, where this R here is given by 0.065, okay? In other words, 6.5%. So this is going to be equal to A of 0 times e to the 0.065t. And what are we interested in? We're interested in finding out how long will it take in order to double our money. So if we start with A0, and double that, then the amount of money which we have at the end will be 2 times the amount that we started with. So, hence, we should look for t such that the equation 2 times A of 0 equals A of 0 times e to the 0.065t. So this is the equation we want to solve. This says we take our initial investment, we multiply by the rate over a given time, and we get double our initial investment. That's what this equation says. And to solve it, all we do is the following. We can cancel out a of 0 from each side, and we get 2 is equal to e to the 0.065t. And then in order to get this thing out of its exponent here, so that I can solve for the t, I'm going to do the ln of both sides. I'm going to take the log of both sides, but I'm going to use the natural log. Remember, that's just log e. And what can I do here? Well, I have ln and e. Those two undo one another, so I get ln of 2 is equal to 0.065t. And this tells me that t should be equal to ln of 2 divided by 0.065. All right. Dang, I always overestimate or underestimate how long it's going to take me to do these problems. So that's how we do this one. We'll return to that example next time and talk over it in a little bit more detail, but I'm out of time. I don't want to hold you guys over. So that's it for today. If you have any questions, then hang around after class and please do ask. Otherwise, I have office hours tomorrow. So yeah, everybody have a great day.
Pretty good.
Yep, thanks, Heidi, you too.